Run through a quick tutorial of how to make these type of nebulas, top to bottom. I'm going to do it as quickly as I know how to do, and hopefully detailed enough for other people to be able to reproduce it. I'm only going to show the first nebula texture because the rest of them can be created by changing around some simple flags inside here. So we'll go ahead and open up the texture. Okay. So one thing that I've changed is I'm using a lot of these double vectors as inputs because there were so many inputs that it was just getting kind of obnoxious to deal with in the material instance. But here we go. So you're going to need an absolute world position node. You need a double vector parameter with these settings right here, 0.1, 0.001, 0.05, 0.6 as defaults. You're going to take the first red value here, multiply it with your world position here. You're going to take the second value, divide it by your object scale, and then multiply it by the world position. And you're going to take your third value. Wait. Yeah. So you're sorry. Yeah. So your third value comes down here, divide by the object scale, and multiply by the scaled world position, like this one is too. Just so that you can see how all this stuff is connected. Okay, so what are we doing? We're scaling the factors we're going to use to determine our UVs. When we finally get right here, this is the world scale scaled times the object scale scaled noise scale, and that goes into the UVs of our first noise node. This is going to be a gradient texture based noise. You can play around with levels to get more performance. This noise node, very important, runs, I don't think I mentioned this last time, it runs from -1 to 1. Okay, so the output of this is going to multiply by the fourth value here, and then it's going to add to this multiply node right here, which is the second value divided by the object scale times the world position, gets this value added in. These are new that I added since the last time I demoed this. This allows you to add a UV offset. This lets you scroll the texture around manually. And it's just a vector parameter that plugs into an add node right here. And then this gives you the ability to animate. And what this is doing, you have the time node. We're multiplying that by this value, which defaults to 0, which means there's going to be no animations. But if you increase these values on any of the X, Y, or Z, increase these values on any of the X, Y, or Z, it'll start animating the noise in that direction. If you use this last value, it will work between the just scrolling animation and a sine animation, which means it'll kind of like wave back and forth. So you can change this to make it go back and forth, and you change these to change the axis it's animating on in the amount that it's animating. Finally, you have another noise node here, similar to the first noise node. I'm using 8 levels. Gradient texture based. You want to use either this or computational. The only difference here between this noise node and the last one is that this is 0 to 1 instead of -1 to 1. We use -1 to 1 for our UV manipulation and 0 to 1 for our actual output. Alright, so we break the noise out here into its component parts, so we multiply them together to get a nice pattern. And then we run that through this remap value range node, which allows us to basically spread the output of that noise to whatever range we want it to be in. My default value is here, 0, 0.25, 0, 1. And then here, similar to what we did with the sine, we 1 minus this, and then we have a field that allows us to work between the 1 minus noise value and the noise value. This allows us to get a little bit more variance for free. And then that runs into this clamp node right here. And this is noise clamp min, noise clamp max. Right now my default values are 0 and 2. And then after that, We take the last value here, which is our new maximum, divide it by 2, subtract the clamped noise value from it, multiply it by 2, and then multiply it by 0.05. The reason we're doing this is we want to... I'm trying to think of like how to describe what's going on. Basically, we're doing the same kind of distortion on a sphere mask that we were doing on the noise. So what we end up with is like a noisy sphere mask that'll be like kind of an amorphous sphere mask. And for that reason, the radius has to be a lot smaller than I initially had, and the sprites have to be a lot bigger, because you don't want your distorted shape to clip the edges of your sprites, because that'll give you artifacts. So I have it set at 0.5 for the B here, B node. The radius at 0.15, that makes it smaller, and then the hardness at 0, so it's nice and faded. I have this smooth step value. This is to clip out the black from our sprite template. And then we take our noise and our sprite and we multiply those together to get our opacity and emission masks, right? And then up here, we're taking our noise output, raising it to a power color mask exponent, the fourth value here, multiplying it by the color mask multiplier from this input. So these are also double vector parameters. So color mask exponent goes into this power, color mask multiplier goes into this power, and that goes into the UV for this custom gradient node, which I'll show when I finish reviewing the rest of this. Color 1, 2, and 3 multipliers simply get multiplied by their respective colors before being fed into this gradient. Okay, and let's see. So this gradient node is a custom node. The code looks like this. If you can't read it, it's float3 call equals lerp blah blah blah. I think I pasted it. It's this. And put that code in here. Rename your members A, B, C, middle UV grad, and then hook it up as you can see right here. So the noise clamp min and max go into this clamp. The color gradient center feeds into the middle node of this node. And then the 3 here is the color gradient power that's going right here. Finally, the output of this node, this is what's giving you your color variance, gets multiplied by our noise mask multiplied by our particle mask, sprite mask. Then we raise it to the emissive exponent and multiply it by the emissive multiplier and plug it into our emissive. Likewise, the same thing, the noise goes in, the noise without the multiply by the color goes into this power node, and it's raised to the opacity exponent and then multiplied by the opacity multiplier, and that plugs in right here. And that is pretty much it for the material. Oh, the other thing, this object scale, this is important. So this scales our UV sampling based on the size of the object, and this is what allows us to maintain a consistent nebula even when scaling it up and scaling it down. So say I had something and I fiddled around with it and I like the way it looks on my system sized at 1. And then I scale my system up to 100 because I want it to fill a scene, and it looks like crap at that point. And the reason is since this texture is world scale based, world position based, and not texture coordinate based, when you make the object bigger, the texture stays the same size. It doesn't scale with it. What does this object scale factor do? Well, what it does is, if I were to scale that same nebula, I get it the way I like looking at 1, and then I scale it up to 100, and then I go plug 100 into this object scale, then that will change my textures to be consistently scaled relative to the size of the object. That is pretty much it. I will go ahead and give like a zoom in flow through the whole thing so that you can pause it at any time and kind of see the way things are connected and be able to work it out yourself. Yeah. Noise settings are important here. This is all core functionality. This isn't using any plugins or anything. Just core material setup stuff. Back over here, and then finally up here. Okay, and that covers the material. So let's go ahead and see this again. And again, there's two here. This material is this one on the right. And this material is Nebula Turbulence. That's the last thing I'll talk about. The only difference here, and I have 4 different materials set up, is in these noise nodes, there's turbulence checkboxes. The default material I've made has none of them checked. There's 2 noises, so 1 noise there, 1 noise here. Neither one has it checked. On the turbulence, this one over here, they're both checked. And then the other 2 materials are one or the other checked. And that's it. That's it for the material. So let's take a quick look at the particle system that we use to build that material. Okay, so the most important thing here is going to be the user parameters. Form mesh, jitter amount, max sprite size, min sprite size, particle count, scale factor. Okay, we're going to use these in our emitter, or in our noise component. Our properties look like this: local space, determinism, GPU compute sim. It's a GPU thing. You can use this to change the bounds at which it'll be visible. So the particle system will be visible as long as the camera has these bounds on its screen or it's inside of these bounds. So if you ever have these bounds set too low, you'll notice that when you turn away from your noise, it'll all of a sudden disappear. That's because your bounds are off the screen at that point. Persistent IDs and combined event spawn, just because we are only spawning once, so there's no real reason not to. Okay, so that's the emitter properties. Emitter state looks like this, real simple. Spawn burst looks like this. Make in from float, particle count, spawn time, probability, loop count. That's it. Initialize particle. Okay. You may notice the scale factor. That is similar to the scaler in the material. It's used exactly the same way. If I size this up, if I got it looking the way I wanted to at 1 and I scaled it up to 100, I would then need to go update my material instance scale factor to 100, and I would need to update this scale factor to 100 in order for everything to scale properly. Sprite size mode, random uniform. Minimum is a multiply float, where you're multiplying the min sprite size by the scale factor. And maximum is the max scale sprite size times the scale factor. Pretty simple. We have a sample static mesh node here that's pointed at the form mesh. This allows the user, the person building this, to supply a mesh object to shape the nebula the way they want. Right now, I just have them unpopulated, which means that they're just a circle, basically being generated by the jitter. But eventually you would want to put in you could put in like a big ring or something like that going around your stage, and then you'd have a ring nebula. Or you could kind of put in some blobs and have blob shaped nebulas. The whole idea of this is that you can change the shape with a mesh of this thing. Okay, static mesh location. This is just normal shit. You just add this default node and it should look like this, I believe. You have this jitter position, multiply float, jitter amount times the scale factor. Again, from over here. Particle state. Let's take a look. Loop particles life to everything's off. Everything's off. And this is a infinite lifetime particle. Trying to find it. Loop count limit. I don't remember where I put that, but like basically you just want it to spawn once and not spawn anymore. So infinite lifetime particle. They don't go away. And finally, you come down here to the sprite renderer, and the only thing you got to do is you got to pick the material instance for the material that we just went over, and this will apply to your particles. The material instance is sampling that noise in three-dimensional space, which is why we get volumetric effects with this, where when I go up close to it, it's... Oh, there's that, what I was just talking about. So, like, the bounds of this are smaller than the bounds of this one. This one's set at, like, 1,000,000, and this one's set at, like, 1,000. So, whenever those bounds completely disappear from my screen here, you can see this disappearing. But I could change that, I could fix that by changing the bounds of this to be a lot larger. So you can see it is a volumetric effect. There is some issues with artifacting as you change color, as you change camera angles. It looks kind of cool. If you don't mind the effect, then whatever. If you don't like that, then you would just use these for like cube maps for skyboxes and things like that. All right, and then so that goes over how